Okay, right. As I said, good afternoon, everybody, and thank you for coming. I've been asked to describe what I'm doing with the DATVExpress project, because some of you won't have heard about it. So I'll try and keep the technical side of it to a minimum, because I just really want to introduce the project. A lot of the technology is the same with DigiLite as far as the theory is concerned, so I won't go too deeply. Right, let's see if this works. Right, okay, well, here, that's me, and that's my email address if anybody wants to talk to me afterwards. And right, now, these are the main members of the project team. They're mainly Americans because I thought there's not much digital activity in the United States, so if we make the thing look as if it's American, it's quite likely that they might be interested in obtaining them. I won't say buying them, but obtaining them. So the program manager is Ken. He does all the talking to various people, and I managed to get him to do the presentation last time rather than myself. But he's obviously not here, so he won't be able to do it. Art is the hardware engineer. He's done all the hardware design, and I thought I'd let him do that. He's done all the I should say circuit diagrams, but he keeps on calling them schematics. So he's done all the schematics on the project, and the next member of the team, and who I think is the most important, is Tom, who's the PCB layout guy. He does this he's professionally involved in PCB layout, so we've got a good guy doing it. I'm not very artistic, so my attempts at PCB layouts look like spider drawings rather than layouts. And finally, myself, I'm doing all the software, both the PC software, which at the moment is in Linux, the FPGA code, which does all the filtering, and also the code that runs on the USB 2 chip, which is an 8051 combined with a USB 2 interface, and that's done in assembly language. Right, aims of the project. So what we wanted to do was to significantly reduce the price of digital television. Obviously, most of the audience knows how expensive it can be, and thankfully the DigiLite project's come along, and that has significantly reduced the cost of things. But I wanted to do my own one, so that's why we're doing this. Yes, provide an open platform for future DATV development. All the circuit diagrams, the Gerber files for the printed circuit board layout, the source code for the software, the FPGA code, it's all going to be made available. Hopefully, people will want to look at it at least, and possibly change it and add to it and produce their own variants of it and just generally learn from it. The next one was help educate the community about new technologies. Well, this is all new, and I wanted to learn about field programmable gate arrays, so this seemed an ideal project to do it on. And I hope other people will learn about these things. I really cannot emphasize enough how wonderful FPGAs are for doing this type of stuff. Obviously, it's not like programming a normal microprocessor, because with FPGAs, everything can happen in parallel. That's their real power. Get more DATV stations on the air. Well, obviously, that hopefully is a side effect of the thing. Encourage more people to get licensed. Well, I'm thinking of non-traditional people coming into the hobby, because if you look on the internet, video and anything to do with video is very, very popular. People are doing all sorts of things, not radio-oriented. Hopefully, with the combination of radio and digital systems, we'll be able to get non-traditional people involved in the hobby who can bring in skills that we may not necessarily have, like composing videos and mixing and all sorts of video effects and stuff like that. We can but hope. And finally, I must stress that this project, it's a software-defined transmitter. It's not just a digital television transmitter. It's basically like a sound card that operates in the 23 SEMS band, and the D2A converter that we've got on there will operate up to 125 megasamples per second, so it's capable of a very wide bandwidth. We are only using it for bandwidths up to 8 megasamples per second, and that's mainly limited by the USB 2 interface. Now, my involvement in digital television all started when I bought a USRP2 from Matt Ettus of Ettus Research. Matt is in fact a radio amateur, and I met him in 1999 at a digital communications conference. He was a student then, and he's gone on to form a multi-million-dollar company, which was recently sold to National Instruments. But these things, these boxes, they're being used for all sorts of stuff. There's software to turn them into mobile radio base stations. People are using them for MIMO, and they're used quite a lot at universities. And I understand some companies and some organisations are buying them and giving them to their new graduates and saying, look, play with this. But I won't go into too much detail with the USRP2 because that's a talk in itself. They are expensive. The one I bought cost about $1,700. That includes the RF board, which will operate between the current one I've got, 400 megs and 4.4 gigahertz, anywhere in that spectrum range. And it produces about 50 milliwatts output over that frequency range. But it is an ideal thing to use for prototyping systems. One disadvantage it does have is that it has a fixed sample rate for the D2A converter, which means that you've got to do interpolation and you've got to change the sample rate in your own code, which is a significant overhead, and DATVExpress gets around that problem. Right. Now, this is just a general overview of the system as a whole. It's, as I said, it's very similar to Digilite in its components. We start off with a video source and an audio source. Those are then fed into a commercial MPEG-2 encoder, if you're using MPEG-2. We're using the same one that the Digilite people are using. It can be done in software as well, but that does produce quite a significant processor load. The PC, which is running Linux, that just takes the video stream from the encoder and converts it into the correct format for what we want. It adds the SI tables, which identifies the program information. It identifies the identity of who's transmitting, what encoding schemes it's using. These things are all needed to make it into a valid DVB signal. The Linux system also, at the moment, it's doing most of the signal processing. It's adding the forward error correction and the code puncturing, which weakens the forward error correction, but it means you can send more data at a particular given symbol rate. And it also maps the INQ, which is the actual RF or sort of analog baseband part of the thing. Any waveform can be represented by an in-phase and quadrature signal. Right, now we go on to the bit that really is what I want to talk about, which is the DATVExpress board itself. The DATVExpress board is an FPGA-based board. It talks to the USB interface to get the information from the PC, and it does all the filtering, the raised cosine filtering, and maps the signal onto the modulation. And then, of course, you need RF amplification. The board itself has a about plus 17 dBm amplifier on it, and then that would then go into an external power amplifier. Right, I've just gone through all of those. You can tell I haven't actually rehearsed this. The obviously the USB 2 interface uses a Cypress chip, as I said before. This is an 8051 microcontroller with a USB 2 interface built into it. It also has got an I2C controller on the chip, and it's got an RS-232 serial port if that's your thing. The field programmable gate array that we're using is from Altera, and it's a 144-pin device, and it has a number of hardware multipliers which are very useful in the FIR filters. Obviously the board provides clocks. It provides clocks for the USB interface and for the FPGA, and also for the modulator. The modulator that we're using is a combined phase lock loop, fractional N, phase lock loop and modulator in a single chip from Analogue devices. It's the ADRF6750. It operates between 950 megahertz and about 1.57 gigahertz, but it also has the ability to take an external VCO so that you can you'd be able to operate it on 2 meters if you wanted to add an external VCO for that frequency range. You can either just inject the signal, which has to be at twice the operating frequency, or you can actually use a VCO controlled by the chip itself. So you can use all the internal logic inside the chip to produce the phase lock loop. The buffer amplifier is a GVA84 Plus, which I think is a 20. We're using at about 20 milliwatts output. We've got an option on there. As it stands, the board will generate the standard symbol rates that are used in the UK, but the Americans wanted to use some peculiar symbol rates. I got the impression that what they want to do is to see how much spectrum they've got and then use the symbol rate to fulfill that spectrum, and it's up to the people receiving to sort the receiver out. That's why we've added the ability to add an SI570 symbol rate generator. Those are the chips which are most commonly used by the QRP fraternity for their radios. We, in fact, are using the chip for what it was designed for, which is a programmable baud rate generator. Obviously, we've also got the DC power supply. The board will operate between 8 volts and about 15 volts. You could probably run it a bit higher or lower, I'm not sure. I run it at 13.8 because I have one of the only 2 prototypes in the whole world at the moment, so I don't want to blow it up. Right, I've really gone over most of this. This is just a diagram of what's actually on the DATVExpress board itself. Yeah, I've got one. Yeah, I just haven't been using it, that's all. I've already been through this, so I shall quickly go through it again. You've got the USB 2 controller. It has a 24 meg clock. There's a boot ROM on there, which we're not currently using, but that can be used to identify the USB 2 controller, because at the moment the chip comes up with its default PID address, and the flash memory can change the PID, and also it could boot from that flash memory. But at the moment I'm downloading everything from the host PC when the board starts up. Obviously, power supplies. There's the FIR, the FPGA. It's all these letters, and that does basically it reads from the FIFO that's produced by the USB 2 controller. The USB link comes in as a serial link, and then it appears as a parallel port on the USB controller. We're using it in 16-bit mode. A lot of people use it in 8-bit mode. That is then read into the FPGA. It goes into a FIFO inside the FPGA, so to give some buffering, so that if there's dropouts on the USB 2 link, we won't lose continuity of the signal. Also, I discovered that it's essential, because that is operating at one clock frequency and this operates at a different clock frequency. Principally, this operates at a clock frequency which is related to the symbol rate. You have what they call metastability problems. So when you transition between the two clock rates, you've got to use some clever circuitry in the FPGA so that you don't get a clash between the dissimilar clock rates. Fortunately, on the design tool, there's a box that says add metastability. So when I hadn't got that clicked, I was losing the signal every now and again in a totally unpredictable manner. When I clicked that button, all was light, so that's very important. Then we go on to the D to A converters. This is we're using an AD9767, which is a dual A to D converter. One is the in-phase channel and one is the quadrature channel. These can either be used, they're 14 bits each, and you can either use them with two 14-bit ports, or we're using them in an interleave mode, where one 14-bit port interfaces between two. It does the I channel, then the Q channel, the I channel. The reason we've done that is we've only got 144 pins on the FPGA, and grabbing 28 pins of those 144 pins just for the D to A converter was more than we could deal with, because we've chosen as lower powered FPGA, i.e. as cheaper FPGA as we could get away with. I think the chips are about $6 each, the particular one. Then, of course, it goes into the fractional PLL. We've got some low-pass filters in there to stop aliasing. I won't explain what that is at the moment. The output of the analog, at this point we've got an analog I and Q signal. That then goes into the modulator, which has a 20 meg reference, which is multiplied up, and the output then goes to the buffer amplifier and then to the SMA connector. And we've got some little LEDs on there. When the board comes up, it flashes. If it doesn't flash, this means there's something wrong. Maybe we'll put some Morse code in there so it says what's wrong. But we've been trying to keep the parts down as much as possible. And the hardware engineer, every time I want to add something, I wanted to add 2 0-ohm resistors yesterday, and he wasn't too keen on the idea. So you get some idea of what we're trying to do with the cost of this. All right. Here's the board itself. I've got one in the demonstration area, but it's inside a box. Maybe tomorrow I'll release it from the box. It's just that there's a load of Vero wire all over the board at the moment, and we made some mistakes. And the Vero wire is carefully hand-soldered by me, and it's not something I'd want to do again, because these pins are very, very close together, especially the pins on the modulator. Right, I'll go over the actual components on the board. That's the USB 2 connector, obviously. There's the 24 meg oscillator. That's the flash EEPROM. That's the USB 2 controller stroke 8051 microcontroller. There's the FPGA. That's the D to A converter. There's the 5 meg low pass filters. That's the phase lock loop stroke IQ modulator. There's the RF output, and there's the power supply. The next board, I've got them to move the power connector onto this side. The SMA connector will be a 90-degree one, and the board will be somewhat smaller. This connector will no longer be there, neither will that connector. This connector here is to connect to the push-to-talk line, etc. And that there is the JTAG connector, which I was going to remove, but I suddenly found is very, very useful, because the Quartus II development environment that I'm using to develop the FPGA code, it allows you to have a logic analyzer. You can download a little bit of code into the FPGA, which then sends back to the development tool what's going on the various lines. So effectively, you can have a hardware analyzer running over the JTAG connector. So that's now is going to be left on the board. Right, overview of the PC software. Operating system at the moment is Linux. I've got it running on 64-bit Linux outside, but my main development system is 32-bit Linux. It's quite interesting, the difference between the two. Code that runs fine on the 32 won't run on the 64. The 64 tends to be a bit more critical about your coding. The PC downloads the FX2 firmware first. That's the firmware that runs on the USB/8051 controller. Then once that's loaded, it then downloads the FPGA firmware via the EP1 interface. The FX2 controller chip actually then writes that to the FPGA itself using a couple of parallel I/O lines. Once the FPGA firmware has been downloaded, the EP1, which is the endpoint that we're using for this, then becomes an I2 I2C interface. So from that we can control the 1.3 gigahertz phase lock loop stroke modulator. We're also going to use that to control the symbol generator, because that also has an I2C interface, and also for offset calibration, because the D to A converter, there's almost certainly going to be an error in the offset on it, which has to be calibrated out. And in fact, for every different frequency, it should be calibrated out. But we're not actually going to do that. We think we can get away without doing that. And then it provides the graphical user interface. This I've all explained before. The transport stream stroke program stream. It's interesting that Halpage, I should say, they do an MPEG-2 encoder and an MPEG-4 encoder. The MPEG-4 encoder produces a transport stream, and the MPEG-2 encoder produces a program stream. The PC software will convert that. It will add the PIDs that are required to turn it into a valid television signal, the PMT, the PAT, and all of that, which I'm sure someone else will explain, which is the SI tables. And I must admit, going through all this DVB documentation, some of it is very confusing. It adds the FEC, it does the interleaving inside the PC. We're not doing it on the FPGA. Obviously, we've got to keep a constant symbol rate. The way we do that is that the material we're transmitting, which is the video, audio, SI tables, is slightly less than the capacity of the link. And then every now and again, we top it up with a null transport packet just to keep the thing operating at the transmit symbol rate. At the moment, the software generates IQ symbols. These are 16-bit symbols which are going across the USB 2 interface. Now, that is not a very efficient way of doing it, but it simplifies the software. Eventually, we'll probably either have a bit stream going across the interface or possibly a transport stream, and then we'll do the unpacking inside the FPGA. Finally, we use endpoint 2 to communicate the video, the actual data that we're transmitting. This is what the graphical user interface looks at the moment. It's a pretty simple thing. It probably could be completely rewritten before it actually goes out into the wild. At the moment, you can see I'm showing off in that it's transmitting a DVB-S2 signal. I only got the software to do this working last week, so that's why we've got a demo with the S2 rather than the plain DVB-S. The symbol rate's at 4 megasymbols, and we've got 1, 2, 3, 4, 5, 6. With the 5.6 FEC with 16 APSK, which is 16 points in the constellation, we've got a video rate of about 10.6 megabits per second, and the frequency is operating on 1.249. The level is 47. There's a 47 dB attenuator, programmable attenuator, inside the modulator chip, so that's why it's at 47. It means that that's the maximum level down. I mean, I've reversed it, so 47 is in fact zero attenuation, mainly because on the USP2 version of the software, 20 is the maximum, so I wanted to keep them sort of consistent. Obviously, we've got a transmit-receive button. That's giving information as to how many nulls are being inserted into the stream. That is the size of the queue, the transmit queue. It's designed to be kept at about 50%. So when it goes below 50%, nulls are added. When it goes above 50%, I start getting worried because there's not much I can do apart from change the video source rate. Here we've got a few error messages. Well, these are just telling you what's going on. I've got a viewport in the software that allows me to monitor the transmit, but it's not set up, so it says it can't open the port. The PVR, it says it's configured it, so no error. Whoops, I don't know what I hit then, but it's all gone dark. Oh, no, we're back, right. And it says firewire failed because I've added code to support a firewire interface, but there's no firewire plugged into the PC, so it says it doesn't like it. Yeah, well, as I explained before, the hardware, we've got basically an I2C interface that controls the PLL, etc., and it does the filtering and talks to the USB interface. The FPGA code is written in Verilog and uses the Altera Quartus II development tool, which is free software. I think it's a couple of gigabytes download if you want to download it. But there's an awful lot of stuff in there, and they support loads of different FPGAs. They support their own NIOS processor. You can have a soft processor running on the FPGA, although ours isn't really big enough. Obviously, I've already explained this before. The channel filtering is an FIR filter, and it's done within the FPGA, so we get crystal clear filtering on the output. This is just an overview of the minimum. This is the minimum that we're going to provide. DVB-S protocol, QPSK modulation. That's the range that the chip will do, but obviously it's going to be limited to what's available in whichever region. The symbol rate, I've been told, has got to go between 1 megasymbol to 5 megasymbols per second in, I think he wanted about, I don't know, I think it was 100 hertz or 100 symbol intervals or something. The forward error correction, obviously selectable, blah, blah, blah. Because it's for the American market, it's got to support NTSC, but really it's the Halpage MPEG encoder that does that, so that's just really not that relevant to me. And operating systems, first it'll be for Linux, and then maybe Windows 32, although I'm going off Windows the more I do with it, and every time a new version of Windows comes out, it makes it more difficult for hobbyist programmers to program. Current project, well, we've got the first PCB built. I've got that outside. Obviously, we've got the Linux GUI working. DVBS is working. I've got an implementation of DVB-T, which I've verified with a television set. Obviously, my TV will go into the 77s band, so under suppressed radiation conditions, I did some tests with DVB-T on the 77s band. It supports at the moment 6 and 7 megs. It could do 8 megs, but we don't have a clock on the board which gives the correct clock frequency, and the internal multipliers and dividers inside the FPGA wouldn't allow me to derive the 9 point whatever it is meg clock that's required. Obviously, we've got the basic FPGA working, and the version 2 PCB should be available to go to the PCB factory at the beginning of December, I've been told. This is the very first picture of the whole system working. It's being received on a set-top box. We've got there's the Express board lying on my desk, all that keyboard and everything at the back, and as you can see, it's on 1.249. The 11-bit is for the benefit of the STB that thinks it's talking to a LNB on a satellite, and the channel is ham1. This is the output of the on DVBS with the raised cosine filtering. That is due to a mistake I made in the maths. I had the wrong instruction in there, and I haven't updated the photograph, so that no longer exists, that bit. This constellation is pretty poor, but the reason it's so poor is we've got a problem with the noise on the synthesizer. It's 50 dB worse than the manufacturer says it should be, but that's hardware and it's not my responsibility. Here's two examples. This is standard DVBS and QPSK, FEC of 3/4, and that's the lowest error rate that my little satellite box will display. Here is my show-off. This is DVBS2, QPSK again. I'm using a roll-off of 0.2 on the filter this time, as against the 0.35, and the FEC rate is 3/4. Now, this wasn't done on the Express board because of the synth problem. This was done on the USRP2. This is 32 APSK, so there's 32 things in the constellation. We've got an FEC of 8/9. The roll-off at this one is 35, and the error rate again is the best that the little box can do. Now, this is the spectrum of the DVB-T signal. Now, you'll notice two problems with this. One, because of the DC offset in the modulator, we've got a spike at the carrier frequency. That will be calibrated out when I've written the calibration routines. I can't do them at the moment because there aren't the wires on the board. They'll come in the next version. Now, the ripple here is due to the fact that I haven't got enough coefficients in my filter that I'm using. Currently, the FPGA is only operating its filter every other clock cycle, so I can double the number of coefficients in the filter quite easily, and my computer program tells me that if I do that, the ripple will drop to about 0.1 dB. So I thought I'd put this slide up here because it shows a couple of the problems that one can get with the approach that we're using. This is me transmitting 7 megs DVB-T and on 1.3 gigs. This was actually done with the Express unit, so it's that grotty spectrum we had before, and I'm using one of the Elonix-based E4000 USB dongles and DVB Dream to receive it. So the dongles will tune into 23, but they're not much use below 1.3 gigs. What else? What about DV? Well, we've done DVB-T. We've done DVBS2. Being for the American audience, they obviously want 8 VSB. I don't think I'll bother doing that. They can do it themselves. Because it's a software-defined transmitter, all these things are possible. It's just software. I have to add that since day before yesterday, suddenly I was told that they want DVB-C as well, because apparently some people in California have been taking cable TVs and doing tests amongst the mountains in California, and have found even DVB-C seems to work quite well. We're only committed to DVB-S in the first release. I've already got more than that working. I've added support for FireWire. The only problem is to use the FireWire, I'm having to use FFmpeg, which uses up quite a lot of processing, because I've got to take it from the format, the digital video format, turn it into an analogue picture in memory, and then re-encode it either as MPEG-2 or MPEG-4. There's a lot of work involved. It works on my very high power development machine, but it won't work on the laptop. Also, using the filters that are available in FFmpeg, we can add text overlays, test cards, and I've done some tests with 1080i HD over DVB-T. Just using an off-the-shelf television set works fine. I'm only using I because that's all the Halpage MPEG-4 encoder will do. It won't do progressive. I've been asked to add this by Noel. Yes, it is possible. The Pi has a H.264, i.e. MPEG-4 Annex 10, I think, encoder, decoder hardware on there, and they are going to enable that because they've been told by the MPEG licensing people that they already have a license for the encoding and decoding. Shortly, I believe, I've been told this morning that sometime before Christmas, they'll have a 5 megapixel camera that will plug into the board. So that will be a source of video. Obviously, it has a USB 2 interface on it, but it doesn't have any onboard sound in. That would have to be an external codec of some description. So what we need to do to use a Pi with our board is we need to convert the H.264 data, which is a raw bitmap that comes out. I spoke to one of the developers at the Pi Foundation, and we'll have to do the formatting to turn it into a valid DVB stream. We'd have to move all the DVB-S encoding onto the FPGA. It's possible to do it for DVB-S, but there's not enough memory on the chip we're using for anything else. Obviously, the longer we leave it, the easier it becomes. It's like everything in engineering, because somebody else will do all the donkey work for us. And as I said, we will have to move the FEC coding onto the FPGA. Right, this is the last one, I think. I've got 6 minutes left. We hope to have the final production around Christmas time. I've been told that the revision 2 board will be posted to me at the beginning of December, so I wait with bated breath. All the software will be released. I've already added DVB-S2. I'm not going to do DVB-T2 because I don't think there's any demand for it, and the spec is very thick, and I just can't be bothered. Now, this is something I've added. I'd like to actually have a go at writing some FPGA code to actually demodulate the signal, because it's a bit more demanding than doing the transmit side. But there's no budget for me to do this. I'll probably have to do it on my own, out of my own pocket. Finally, if you can read that, that's my blog. I write about how I'm getting on and all the various things I'm trying, and I'm desperate for followers on Twitter, so I'm sort of about 147, and they keep on going away, and most of them are young, partially clad young ladies. But I think we've got one more slide. Right, there we go. Thank you all, and I've got 4 minutes left. I don't know whether anybody wants any questions. Any questions? Yeah, well, I can't wait to get the version 2 board. It's,
There is one question, actually.
yeah.
It's fantastic. Can't wait to get bored. One question, of course, the IQ modulation, so many options. So how about a bit of DRM and a bit
well, you could
DAB?
do, but
Can't be that difficult.
well, someone can write it. I mean, I think there's DRM receive software available, but and also all the various novel modes that people are coming up with, we can do it. It's really the receive side that's a bit more of a problem.
Spark actually is Spark for the DRM transport stream, so one assumes it'd be pretty easy to interface.
Yeah,
straight
I'm actually talking to somebody that's implemented DAB on a USRP2, and he's very keen to play with one of these, so he might get DAB on it. I'm not quite sure why. I thought Andy was asking a question.
That phase noise problem, you said 50 dB worse than the manufacturers.
Yeah.
Any idea why?
No. Off camera, the hardware engineer left the filter out when he did the board, and so he had to put it on by hand. And there's little bits of wire hanging all over the place with sort of prongs like that with capacitors attached at the top and things like that. We're using the circuit that's in the manufacturer's application note, so it should work. Oh yes, I know. It's just purely a hardware problem. It's something to do with the board layout. But as I said, I'm a software engineer now. I'm no longer a hardware engineer. Right, is that everything?
Okay, thanks, Charles.
Right,
big round of applause, I think.
Thank you.
Okay, and